Chapter 4, we're going to start with section 1 here on exponents and their properties, but what this whole chapter is going to be about is polynomials. Nomial means terms and poly means many, so we're going to be talking about terms, which are probably the best definition of a term is the parts that are being added in an expression. Okay, so like in this expression up here, I have 3x squared minus 7x plus 5. Well, the addition, if I ask for the terms for that, that would be 3x squared, a negative 7x, and 5 would be the terms of that polynomial. So, and we'll go through this more as we get into combining like terms and a lot of other stuff. But we're going to review, this should hopefully be a review of exponents and at the beginning what exponents are, but also we're going to go through some rules that basically are shortcuts to see that there's really some patterns of how we can work with exponents of like bases. And again, what that means is a base is the part that is the multiple factors. An exponent or a power, just to remind you what that means here, I'll break this down here. They're really going in here with like bases, and if you don't remember what those things means from either Math 93 if you took it in there, but in the prior chapters of this book they talked about exponents or powers. And the base is the factor that's being multiplied multiple times, where the exponent is how many times is a factor here. A is the base, and the 3 here exponent is how many times a is a factor or part of this multiplication. And they're just showing us some examples. So if I have a to the third times a to the second, I could really write this out this way. And then if I think about, I can break the parentheses by using the associative property, really. I'm not changing any order like for the commutative property. And I end up with a times a times a times a times a, which is to write that as an exponent, or as a power, with the base of a, the exponent would be 5, because a is a factor 5 times. And it looks like, and the rule that they're going to give us basically is, if I have like bases, in this case the a's are the same, and I am multiplying, I can just add the exponents as a shortcut rather than have to write all that out, make sure I count right, and make sure I put the exponent right. They show another example and they say, hey, it looks like we just add the exponents. And that is exactly the rule here. And here's the rule in this box here. It says if I have a to the m power times a to the n power, notice that the bases are the same, both a in this case, then I can just add their exponents. I can say it's a to the m plus n, or this exponent plus this exponent, and I can shortcut that, take less steps when I'm working with these exponents, and use these product rule for powers, and take the shortcut, and basically less steps, less chances for error. So in these examples, that's what they're working on here. A couple interesting ones are a little harder ones to see. And they picked these examples for some reasons too. These cautions are very important. Please pay attention to these. I see this every time I'm correcting tests, these kinds of errors, and that's what they're trying to do. These cautions are about common errors, especially when you put numbers in there. So when I have like 2 to the third power times 2 to the 8th power, that is 2 to the 3 plus 8, or 2 to the 11th power. It is tempting to say that, hey, I can multiply 2 times 2 and get 4, and say it's 4 to the 11th. Well, 4 to the 11th power is completely different than 2 to the 11th. Do that on your calculator and see how much different that is in the actual answer to that power. There's a huge difference. Okay. So the other thing too is when we have no exponent like this one here, where we have 5 to the third times 5 to the 8th times 5, we need to remember that if there's no exponent there, it's the same as the 1 power. It means 5 is a factor once. This means 5 is a factor 3 times, this means 5 is a factor 8 times, and then one more 5, which means it's a factor 1 time. So we can add that as long as you remember there's a 1 there. And they have another caution here, it not necessarily has to do with this 1 power. But it's very easy to go in here and say that it's really 5 to the 12th power is the same as 5 times 12, which is 60. 5 to the 12th power is quite a bit larger than 60. Okay. This is important here too, and this is a little harder to recognize, is when I have something in the parentheses again, that the actual base of this multiplication is this addition of r plus s, and here's r plus s. I need to recognize that this base and this base are the same, so then I can just, when I have multiplication between those, I can add those exponents and I end up with r plus s, the quantity all to the 13th power. And also in here you need to recognize that this works on, we can combine, or basically it's all multiplication, so we could change the order with the commutative properties and change grouping with the associative laws, right? That's why they put this here. And I can make this so I have like bases together and use my rules. Now dividing powers with like bases, when we multiplied we added the exponents. Well, when we divide we subtract. Okay, and they're going to give us some extra rules in here, and they show this drawn out, and I kind of like this. This is very easy to see a lot of problems with fractions. Remember, when we multiply fractions and they write these powers out with all the factors, here is a to the 5th over a squared, right, or a to the 2 power. They say, well, I could rewrite this fraction as two fractions. One is a times a times a over 1 times a times a over a times a. Well, why do they do that? Because I made a new fraction out of that that's equal to 1, and I get this new value. Well, this is the same process you go through when you simplify fractions. So what they're really doing is simplifying the fraction, and they want you to notice a pattern here again, is we ended up with a to the 5th over a to the 2nd, and they want you to recognize, hey, that looks like it's 5 minus 2 is equal to 3. Maybe I have a shortcut here of subtracting exponents, and yes, you do. The quotient rule, quotient means answer to a division, and that's what fractions are, really, divisions. So it says for any non-zero a and any positive integers m and n, for which m is greater than n, and we're going to talk about this a little bit later. They're really just trying to avoid something called negative exponents until they talk about this. So they put this extra condition in here that says that I want my top exponent to be bigger than my small one, so I don't end up with a negative number after the subtraction. And we'll talk about that a little bit later when we start talking about negative exponents. So in these examples here, 7 to the 9th power over 7 to the 4th power is 7 to the 9 minus 4, which is 7 to the 5th. Remember these bases here. When there's parentheses, this entire thing is the base. So even when I get done with this, this should be parenthesis 5a all to the 12 minus 4 power, or 8, right? So I'd have parenthesis 5a parenthesis 8. Okay. And then we can sort out these fractions a lot of different ways. I could say this is 4 over 6 times the fraction p over p squared, p to the 5th, over p squared, q to the 7th over q. So I'm going to look at that and think about that when we go through how they solve this in the examples here. So, this is a pretty straight deal here. They just subtract exponents. Again, they caution you is the other real common error is to think, hey, I can divide 7 into 7 and make it 1. Well, 1 to the 5th power is 1. This is definitely not equal to 1. I have a different number over it. These are not the same. The only way you're going to get a fraction equal to 1 is that the numerator and the denominator are the same. Okay. A lot of errors around this. Where are the parentheses or the base, really? What is the base? Remember that in this case 5a is the base, so it's 5a all to the 8th power, which would be, when we get into further rules, that's a lot different than 5a to the 8th power. Okay, and they show this here too. Remember, multiplication of fractions. I can break these into multiple fractions multiplied together. I'd end up with the same exact thing here. 4 over 6 times p to the 5th over to p to the 2nd times q to the 7th times q to the 1, which is they put the 1 in there to remind you that we're going to deal with that exponent, right? Well, I can do this. These are 3 different fractions multiplied together. Well, if I multiplied them together, what would I get? This original fraction. And the reason they do that is you can simplify each part. Well, 4 over 6, and this is usually forgotten here. You're kind of working on these exponent rules. Well, 4/6 is not a simplified fraction. I can write 4/6 as 2 over 2 times 2 over 3. And I'd end up with 1 times 2/3 or 2/3, okay? And then they do these other ones. So I get 2/3 p cubed q to the 6th power. Or you could write this as 2 p cubed q to the 6th all over 3, and that would be correct too. Now, 0 as an exponent is kind of an interesting thing, and what they do is they say, well, let's talk about things we know that are there, like first this fraction, a to the 4th over a to the 4th. Well, we should know when the numerator is the same as the denominator, we end up with a fraction equal to 1. And that's exactly what they've given us here, is these are exactly the same as long as a is not 0. And you can't divide by 0. So when they're talking about fractions and variables in the denominator, this is the divisor of the fraction, you got to watch out for that 0 because that's undefined. So they usually put that in there. You need to assume or make a rule that we will not allow the denominator to be equal to 0. Well, anyhow, if we look at this again and just go back and say, well, I have the same denominator as the numerator right here. In other words, this fraction is equal to 1. Well, if I apply this rule we just went through, the quotient rule, which is the quotient means answer to a division, I end up subtracting the exponents. I get a to the 4 minus 4, which is 0. So it looks like when I have something to the 0 power, it's equal to 1, and that is true. They give us this rule that I can do that. So like if I went 2 squared over 2 squared, right? It would be 2 to the 0 power if I applied that quotient rule, and 4 over 4 is 1. I could do a whole bunch of examples of that. So anytime I see something to the 0 power, that really is equal to 1. And that's the examples they go through here. If I have 1,948 to the 0 power, that's equal to 1. Negative 9 to the 0 power is equal to 1. And if I have like 3x, the quantity all to the 0 power, then it is equal to 1, as long as x is not 0, because 0 to the 0 power is 0. Okay, so that's the only exception to this 0 exponent rule. Now remember your grouping in order of operations. Since 3x to the 0 power really means 3 times x to the 0 power, the base is x, so the exponent only works on the base, in this case x. So if I have 3x to the 0 power, that whole thing is not equal to 1. It's equal to 3 times 1, which is 3. In this case, if I have negative 1 times 9 to the 0 power, that's really negative 1 times 1, or negative 1. So they give us pretty good examples, trying to kind of give you a taste of all the different ways this thing can happen. Well, the next rule we're going to talk about is raising a power to a power, or an exponent of exponents in a sense. Not very good terms, but and they write this whole thing out. The first thing it says, consider this expression 7 squared, or 7 to the 2 power, the whole thing, the quantity, to the 4th power. Well, if I took that base of the 4 exponent, which would be 7 squared, you'd write it out 7 squared times 7 squared times 7 squared times 7 squared. That means 7 squared is a factor 4 times, part of a multiplication. Well, 7 squared means that 7 is a factor 2 times. So you'd have 7 times 7 in each grouping here, right? Well, if I take the parentheses away, which is the associative property, and then I just write it out this way, what does this mean? It's I got 1, 2, 3, 4, 5, 6, 7, 8 sevens as a factor. Well, that means 7's the base and the exponent is 8. And it looks like there's going to be a pattern here. They do 7 to the 5th all to the 3rd power, and they end up with 15 of them. Well, it looks like we multiply the exponents, and that's exactly what happens. So anytime I have a power of a power, I'm going to shortcut for that is to actually multiply the exponents. So in this case, they show us in this rule a to the m power, or the base a to m exponent, all that grouping of that whole thing to the n power is the same as base a to the m times n, or first exponent times the second exponent, and you get a rule for powers. Okay, so examples of that again, like if I have m squared to the 5th power here, that's the same as m to the 2 times 5, or 10th power. Now, raising a product or a quotient to a power is pretty much the same thing, and they're going to show us a couple ways that happens. And they talk about that is that if I have a product like a times b all to the nth power, it's kind of like the distributive property. But if I wrote this out, it would be ab times ab, right? If this was a 2 times ab times ab, then I can change the order with the commutative. I can then group them differently with the associative property, and I'm going to end up with a to the n power, b to the n power. It's kind of like distributing the exponent over the exponents of the product in this case. Here's an example. So if I have 4a to the 3rd power, that's the same as 4 to the 3rd power, a to the 3rd power. Or if I actually did that, 4 to the 3rd power, it's 64 times a cubed, or a to the 3rd power. And so on. They show you different examples here. You should check them out. Caution again. Boy, there are a lot of cautions in this section. There's a lot of real common errors that occur around these exponents. I can't emphasize enough, if you just really got to concentrate on what the terms mean. So when I have an exponent, what does that really mean? It's going to change the base, and what is the base, and it's going to make it into a multiplication of the bases as many times as that exponent's telling me to, right? So you really got to concentrate on that meaning, and hopefully it'll pull you through. There's a whole bunch of different ways you could create problems around this. I worry about memorize technique, where you're trying to get the problems into something that you can recognize and then take a memorize technique from there. Boy, that's a lot of memorization for I can present a problem about, at least 4 or 5 different ways that would apply exactly the same rules. You'd have to memorize all those different ways, or really concentrate on how the rules work, and then it doesn't matter how many ways I show that problem. Well, it works the same thing with quotients. Quotients, again, are divisions. Fractions are divisions. So they bring up this quotient, which is an answer to a division problem. So if I have this fraction a over b to the nth power, I could rewrite that as a to the nth over b to the nth. Now, a common question is, why do we rewrite all these things different ways? Our goal down the road is to work with these polynomials, multiple term expressions, apply all these different rules, and try to find ways usually to solve an equation is what we're looking for. And we'll talk more about what solutions are. So these are tools in my toolkit. I need to get comfortable with this. I have, been given, a hammer and a nail, and then we got screws, and now we have screwdrivers, and there's different types of screwdrivers and all those kinds of things. So we're going to build something with these tools, and then we're going to have, it's kind of like the variables are our pieces of wood or whatever, to take that analogy a little bit farther. But again, it's about problem solving, and I see so many students are so uncomfortable with understanding the rules, they never get to the point where they can, concentrate on the problem solving part of that, which is really sad, because I see lots of students who are very good problem solvers. It's just that they've only learned how to use a hammer and nail, so every time you say build something, they're going to start hammering nails into something. And there's a lot of different ways and different things we need to do. A lot of times it's, we got to have the right screwdriver to put in a screw. So if you only have a hammer and somebody hands you a screw, you'll get it into the wall eventually if you pound it, but it's sure not the best method and not a very good problem solving technique to build on. Okay, so get these rules down, practice them, think about how you're applying them and how that works, and all those kinds of things. And it's sure not an end into algebra. It's just a tool that when we get presented with, especially equations that we need to solve, that we can apply these rules to solve equations. So I'm kind of trying to jump ahead a little bit to kind of say this is not the end. It's not like, oh yeah, I can manipulate fractions now that have exponents. Well, there's going to be some reasons for that later. These examples are very good to go through here, where they say squaring the numerator and denominator. Squaring is a slang term for the exponent 2, because that's what we measure area in as squares, or something to the 2 power. Well, they use this quotient rule, so they'd say, well, I could rewrite this as x to the 2 power, x squared over 5 squared, and I could actually square the 5 or take it to the 2 power and get 25. Not 10, 25, okay? So on these other examples. And that's about the deal. This is a nice little summary of all the rules that we went through here. They talk about, remember that a to the 1 is equal to a. You got this 1 exponent that's implied there. That becomes very necessary to know what that exponent is, so I can add or subtract it depending on what rules I might be applying. Here's something about the 0 exponent. Anything to the 0 power is equal to 1 except for 0. The product rules here: quotient rule, power rule, raising a product to a power, and raising a quotient to a power. This kind of summarizes all the rules we've gone through, and then in the exercise you're going to practice these rules. Okay. I'll probably say this in a couple videos. I did put an announcement. The chapter 4 test is going to be coming up at the end of this chapter. That'll be our first chapter test. how we take chapter tests are different than what we've gone through with the quizzes. The quizzes, you get multiple attempts over a multiple day window. There's no password on those quizzes. I'm hoping that we'll take it like a pre-test, that you'll at least attempt that quiz one or two times without any outside resources. And it's going to tell you where and how you're going to be able to do on a chapter test. The chapter tests have to have live face-to-face proctoring. This first one I've scheduled room 1033, which is a proctoring room in the Wenatchee campus for February 9th, I think it is. It's in the announcements. If you are able to come in on that day and you're close enough to Wenatchee campus to make it here, that's a nice time to do it. We can get hopefully most of the class. We'll have a proctor there. You don't have to schedule anything if you can fit it into that pre-scheduled time slot for a proctor. Now, for everybody else that is not able to make that time from in the afternoon on that day, you need to arrange your own proctoring, a live to live or face-to-face live proctor. OMAC campus, I know they have some proctoring services up there. You have to call the OMAC campus, set up proctoring. It has to be scheduled by you, and then it has to be approved by me. So I need to find out who you're proctoring with or who you're using for proctoring, especially if you're going off with anything other than the Wenatchee campus approved proctoring or the OMAC campus approved proctoring. You need to make sure that I know who's proctoring, when you've scheduled the test with prior to that, and then I need to pre-approve that proctoring for that test session. You get one attempt on a chapter test, and you'll be able to use a calculator and scratch paper, and that's it, which is pretty important to know. So when you're doing quizzes, that's a good way to do an attempt on that. Your quizzes are worth 30% of your grade. I'm not going to do all 3 quizzes if I'm struggling, and or worse than that would be to use your material, maybe get an okay grade, and and then the last one attempt it without, and then get a really poor grade right at the end of your 3rd attempt of your quiz, and find out, hey, you're not doing very well without any help, really, right? So I would attempt first without help. Maybe you'll do poorly, but you can review the quiz. You can see what types of questions you're having difficulty with, and I would review the material, try to find out what you're doing wrong, and then attempt that quiz again. Hopefully without resources too. Have I prepared? Am I ready for the test this next time? And do it each time like that, and I would think that your grade's going to improve each attempt on the quiz, and you're going to be more prepared for this chapter test where you cannot use any outside material. So I'll probably fill this into a lot of the videos, and but it's important that you could get your proctoring set up. You're going to need to do this for every chapter test. Will be with a live face-to-face proctor, and if you're in some remote areas, I've had some students arrange with libraries that are close, if they have a library in your town, those kind of things. So, but the main thing, I'm not going to spend a lot of time talking to the whole class about that. So if you don't fit into the OMAC or Wenatchee campus proctoring systems, don't work for you, you need to start looking for and arranging with me some alternatives for that. So good luck. Hopefully you did well on your review quizzes, and we're going to go through this chapter and look at your calendar. It tells you the due dates and when the next quiz is coming up. Make sure you're ready for that, and good luck, and I'll talk to you next video.